Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal T equivalent circuit when load details and values of transmission line parameters are given. A three-phase transmission line 200 km long has the following constants: resistance per kilometer 0.15 ohm, inductive reactance per kilometer 0.5 ohm, and capacitive susceptance per kilometer 2 micromho. The transmission line is delivering 50 megavolt ampere at 0.85 power factor, lagging at the receiving end. The voltage at the receiving end equals to 132 kilovolt. We have to determine the sending end voltage and current, the sending end power factor, the percentage voltage regulation, and the efficiency of transmission using nominal T method. Let us first write down the given data. Load SL equals to 50 megavolt ampere, that is equal to 50 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.85 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.85, that is equal to 31.788 degree. We know that load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 50 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3. That gives us 218.7 ampere. Now we shall write down load current in polar form. IL equals to IL at an angle minus phi L, that is equal to 218.7 ampere at an angle minus 31.788 degree. Now we shall calculate receiving end output power. PL equals to SL into cos phi L. Using values we get 50 into 0.85, that is equal to 42.5 megawatt. Given length of the transmission line D equals to 200 kilometers. Resistance per kilometer per phase R1 equals to 0.15 ohm. Inductive reactance per kilometer per phase XL1 equals to 0.5 ohm, and capacitive susceptance per kilometer per phase BC1 equals to 2 micromho, that is equal to 2 into 10 to the power minus 6 mho. Now we shall calculate resistance per phase R equals to R1 into D. Using values we get 0.15 into 200, that is equal to 30 ohm. Inductive reactance per phase XL equals to XL1 into D. Using values we get 0.5 into 200, that is equal to 100 ohm, and capacitive susceptance per phase Vc equals to Vc1 into D. Using values we get 2 into 10 to the power minus 6 into 200, that is equal to 4 into 10 to the power minus 4 mho. Transmission line impedance per phase Z equals to R plus JXL, that is equal to 30 plus J times 100 ohm. Now we shall calculate per phase impedance of half of the transmission line. ZH equals to half of Z, that is equal to 15 plus J times 50 ohm. This may be written in polar form as 52.2 ohm at an angle 73.3 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. We have computed load current IL equals to 218.7 ampere at an angle minus 31.788 degree. This may be written in Cartesian form as 185.895 minus J times 115.206 ampere. We have obtained capacitive susceptance per phase Vc equals to 4 into 10 to the power minus 4 mho, and per phase impedance of half of the transmission line ZH equals to 52.2 ohm at an angle 73.3 degree. Let us now calculate capacitor voltage per phase Vc equals to VR plus IL into ZH. Using values we get 76,210 at an angle 0 degree plus 218.7 at an angle minus 31.788 degree into 52.2 at an angle 73.3 degree. That gives us 84,758.6 plus J times 7,566.3538 volt. This may be expressed in polar form as 85,095.652 volt at an angle 5.1 degree. Let us now determine capacitor charging current. IC equals to Vc into J times Vc. Using values we get 85,095.652 at an angle 5.1 degree into 4 into 10 to the power minus 4 at an angle 90 degree. That gives us 34 ampere at an angle 95.1 degree. This may be written in Cartesian form as minus 3.0224 plus J times 33.8654 ampere. Now we shall determine sending end current. Is equals to Ic plus Il. Using values we get 182.8726 minus J times 81.3406 ampere. This may be written in polar form as 200.15 ampere at an angle minus 23.9792 degree. Sending end voltage per phase Vs equals to Vc plus Is into Zh. Using values we get 84,758.6 plus J times 7,566.3538 plus 200.15 at an angle minus 23.9792 degree into 52.2 at an angle 73.3 degree. That gives us 91,568.737 plus J times 15,489.685 volt. This may be written in polar form as 92,869.607 volt at an angle 9.6012 degree. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 92,869.607 volt at an angle 9.6012 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 200.15 ampere at an angle minus 23.9792 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 92,869.607, that is equal to 160.855 into 10 to the power 3 volt or 160.855 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 9.6012 degree plus 23.9792 degree. That gives us 33.5804 degree. Sending end power factor cos phi s equals to cos of 33.5804 degree. That gives us 0.8331 lagging. Now we shall calculate sending end input power. Ps equals to 3 times Vs into Is cos of phi s. Using values we get 3 into 92,869.607 into 200.15 into 0.8331. That gives us 46.4566 into 10 to the power 6 watt or 46.4566 megawatt. We have obtained receiving end output power PL equals to 42.5 megawatt. Now we shall calculate efficiency of transmission. Eta T equals to PL upon PS. Using values we get 42.5 upon 46.4566. That gives us 0.9148 per unit or 91.48%. Let us remove the load from the receiving end and calculate no load capacitor charging current. ICO equals to Vs upon Zh minus Jxc. We have obtained sending end voltage per phase Vs equals to 92,869.607 volt at an angle 9.6012 degree. per phase impedance of half of the transmission line ZH equals to 15 plus J50 ohm and capacitive susceptance per phase BC equals to 4 into 10 to the power minus 4 mho. Let us now calculate capacitive reactance per phase XC equals to 1 upon BC, that is equal to 1 upon 4 into 10 to the power minus 4, that gives us 2500 ohm. Let us now determine ZH minus J times XC. Using values we get 15 minus J times 2450 ohm. This may be expressed in polar form as 2450.046 ohm at an angle minus 89.6492 degree. Using values we get ICO equals to 92,869.607 at an angle 9.6012 degree divided by 2450.046 at an angle minus 89.6492 degree, that gives us 37.9 ampere at an angle 99.2504 degree. We have computed capacitive reactance per phase XC equals to 2500 ohm and no load capacitor charging current ICO equals to 37.9 ampere at an angle 99.2504 degree. Let us now determine no load receiving end voltage per phase. VRO equals to ICO into minus of J times XC. Using values we get 37.9 at an angle 99.2504 degree into 2500 at an angle minus 90 degree. That gives us 94,750 volts at an angle 9.2504 degree. Let us now calculate voltage regulation, that is equal to VRO minus VR divided by VR. We have obtained receiving end voltage per phase on load VR equals to 76,210 volts. Therefore, voltage regulation equals to 94,750 minus 76,210 divided by 76,210. That gives us 0.2433 per unit or 24.33%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominality equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.